So, hi everybody, thanks for being here to our weekly seminar. We are delighted to hear Thomas Strobl from Lyon speaking about BFV extensions, which is his latest work. So, please, the stage is yours.
Okay, thank you very much. It is my first online Blackboard talk, so I'm curious how this will work. So let's get started. So it's about BFV, or a little bit about BV, and it's a bit the ink is still wet of our last paper, and we will probably still modify it in the near because we are learning more and more about this. So I wanted to, let me see how I can encircle this. Okay. I wanted to start with just probably I should say two, 3 words about BV and BFV in general, I guess. So let me start with this. So in BV, you have the cotangent bundle shifted by -1, if I'm not mistaken, of some graded manifold as your space of fields, or your phase space, which induces BV bracket. And you have your BV functional, which is an extension of the classical action, where so the classical fields are part of this graded manifold M, which has a Z grading if it's induced Z2 grading. And in degree 0, we have the classical fields. And in degree 1, in this extension, you usually have the gauge transformations, maybe I don't write it so much, times the momenta in this space. So the momenta are called antifields, and let's write it like this. And higher extensions such that there's the master equation, which is that SPV in this bracket, I will not write always this bracket if BV is 0, which means that its Hamiltonian vector field QBV is a differential. And one of the main criteria for this to be a valid BV formulation is that its cohomology QBV at degree 0, this should be isomorphic to the functions on the classical equations of motions, modulo gauge symmetries. So let's write it like this: equations of motions, modulo gauge symmetries. It's one of the requirements, and this equation is called the master equation. And since the classical action is of degree 0, so this SPV has degree 0, and since we shifted by -1, the symplectic form has degree -1, then the Poisson bracket or the BV bracket has degree +1, so that this QBV has degree +1. Okay, then there is a Hamiltonian counterpart of this. And in the Hamiltonian setting, so let's say the system, I don't know how to, they're very short, these pages in this format. But you say it's better than if I make it like this, right? Okay, I need to adapt to this format. Okay, so there is this, let me start here. BFV, that's the Hamiltonian counterpart. So there you also have as a phase space or whatever, as a space of fields, a cotangent bundle, but now it is not shifted, so its bracket is of degree 0, but you have a charge Q BFV, which now is of degree +1. And it starts with some goals, which I will call psi A. So these are some of the graded variables, and GA are my constraints, and then there's some continuation. Let me just write the next term. So there's something like psi A. Now let me start with some. So if C, A, B, C are the structure functions of these constraints, the pi A are the momenta conjugate to this ghost psi A. So classically, these psi A's are the gauge parameters in some way. And so it kind of starts with the gauge transformations. And the master equation now has two parts because there's still the dynamics given by Hamiltonian, which will come into the game. So the master equation now is that Q BFV with itself, this charge I make like this is 0. So this is the master equation 1, so to say, and it means that we have again a cohomology which is defined by the Hamiltonian vector field of Q BFV, and since now the bracket is degree 0, but the charge has degree 1, so this is also of degree 1. And we now have the condition that the cohomology of this one at degree 0 is supposed to be the functions on the reduced phase space. So it's the classical phase space and the Hamiltonian reduction by the constraints. But as mentioned before, so there's a second part now. We also have the dynamics given by Hamiltonian. So we have an extension of the Hamiltonian. So this HBFV starts with the classical Hamiltonian and continues like this, and then there's a second compatibility of this extension in such a way that it is Q BFV closed. And that's the second master equation. Okay, so that is so these are these two parts in the Hamiltonian formulation, and there are also nice formulas from for a passage from the BFV to the BV, and they are already rather old even, and they go back to Fish and O. I don't know if I write this correctly. And were streamlined by Grigoriev and Damgard. I'm sorry if I misspell maybe the names. And this is of advantage because in many situations it's rather easy to find the BFV extension of this Q. And okay, in the theories I had experience with, the Hamiltonian was even absent because it was topological theories. And say, for example, the Poisson-Sigma model, the CABC, is just a derivative of the Poisson tensor. It's just a very simple calculation to find it. And then this method yields you this SPVFV extension, which also contains the second derivative of the Poisson tensor. And if you just search it by hand, it's more tricky to find. There is one caveat to this, that so actually, long ago, 20 years ago, when with Klimczyk we found this twisted Poisson-Sigma model, I tried to apply this method, and I found a BFV extension for the twisted Poisson-Sigma model, which was not covariant. So that's why I didn't put it. And then later with Noriaki Ikeda, it was quite some work to find this BFV extension just by hand of this twisted Poisson-Sigma model. And afterwards we went back to this simplified formulas from Fischer-No, Grigoriev, Damgard, and we improved the method such that you can fine-tune these formulas so as to produce something covariant. So this was originally, I was supposed to talk about this, but I wanted to maybe talk about the more recent development, but I still wanted to mention this. So there is some improved version of these transformation formulas, of these formulas from this easier to obtain BFV formulation to the BV formulation, which can be used to establish covariance of the resulting formulas. In some cases, let me write just this keyword, there is this AKZ formalism, which gives you on the nose solutions of the BV or BFV setting just by construction. So there's a natural Q, say on a Poisson manifold, you have the bivector you can view as a charge on the shifted cotangent bundle, which is a Lie algebroid. And so you get a Q there, you have a Q, so a differential on the world sheet, which is the Durand differential. And out of these two differentials, you can cook up an SPV or also SBFV, which satisfies everything on the nose. They're however somewhat limited. So this is only topological, at least in the normal formulation. And even the topological setting, you at least not directly, you obtain this topological twisted Poisson-Sigma model, for example. So this is somewhat limited. At least in the physical sense. And the other thing is, so I have the impression that in fact it actually doesn't always satisfy this condition that its zero cohomology gives the right thing. So it does take into account ghosts for ghosts and so on, but it seems that there's something still missing in this zero mode sector. So if you just take the simplest Poisson-Sigma model, like this one-dimensional Abelian BF theory, I had the feeling that there are some global modes which are not, and actually they are only global modes because it's a topological theory, which are actually counted twice. So, but I didn't look at it in much detail, but I want to say, so there's a natural framework, but it is still not clear to me that this does fulfill the decisive test of the cohomology, which is one of the main criteria of this whole extension. It tells you what kind of ghosts to introduce, and if you have reducibilities of the gauge transformations or constraints, you need ghosts for ghosts and so on. So much as for an introduction, and now maybe I come to the second part, which is where I want to introduce the type of models we want to we analyze together with Sascha Hanschruck, who is doing his PhD here in Lyon, and which is, however, also building on some other work of collaborations with other colleagues. And it's like singular Riemannian foliations as mechanical constraint systems. So this is the classical part. So we are on the Hamiltonian level, and so we need to define the constraints, and we need to define the Hamiltonian, which is compatible with them. And so as for the constraints, so let us look at the following setting. So suppose you're given a manifold M, and you're given on it a singular foliation in the following sense. So that actually is some submodules of vector fields. It's infinity of M submodule, which is finitely generated locally. So locally we have some finite number of vector fields VA, which generated over the functions, and which are closed to this, which is closed the whole set under the Lie bracket. So in particular, this implies that the manifold you have is foliated into leaves, which are generated by these vector fields, but they can in general also have different dimensions. So that is the singular foliation in the classical sense, but here it's somewhat more controlled. And the simple idea is, so first of all, let us maybe rewrite what this last condition FF inside F means for these vector fields. It means that there are some functions C, A, B, C that if I calculate the Lie bracket between locally defined vector fields, then they have to close on these vector fields because they're generating this. So there are some functions C, A, B, C, and right. And now there's one simple observation which we will use also in the second instance again, so that we can identify sections in Tm, so vector fields, sections in Tm, we can identify with bilinear functions on T star M. So, and we will use those as constraints, where the CABC precisely become the CABC we saw before. So if we say that if you have a vector field VA, which is VAI of X d by dxi, then the other side here I identify this with my constraints, GA, which I just put equal to VAI of X, and I replace the derivative for the vector field by the momentum PI, because sections on a bundle are fiber linear functions on the dual bundle. So these are our constraints, and because of the first condition in blue, we have the usual condition, which is called first class by Dirac, is that the Poisson bracket of GA with GB closes on these constraints. So this is the first class property. Or if the GAs define, if GA equals 0 is a manifold, submanifold of T star M, it would mean that that it's a coisotropic submanifold. So that is the constraint system as such. Now we want to add a Hamiltonian, and so the standard Hamiltonian in mechanics is given by a metric on M. So let G be a metric on M. Then we take our Hamiltonian H just in the usual way. So we take the inverse matrix Gij of X, and it's Pi Pj. And it has the property, for example, that it's the flow it generates on T star M can be identified with the geodesic flow of the metric M. So that's our Hamiltonian. And we need also compatibility of the Hamiltonian with the constraints, and the standard compatibility condition is that HGA is some function omega AB GB, which in other words means that H is gauge invariant on this constraint surface, because GAs, the Hamiltonian vector fields, generate the gauge transformations, and GA equals 0 is the constraint surface. So that's the condition. Right, and now one can also ask what this means geometrically on M, this condition. And so we get a metric G as mentioned, and this metric now needs to have some compatibility with the singular foliation on the manifold M, which is encoded by these GAs. And the condition is an algebraic version of a singular Riemannian foliation. So this condition means that, this condition means that the manifold M with the metric G and the singular foliation is a singular Riemannian foliation. In particular, this encodes two situations. One is if you have, if F is generated by isometries, then you would get omega AB equals 0 on the right-hand side. So it would be just even a strict invariant Hamiltonian, at least in the adapted choice of these representatives generating the constraint surface. Another option is Riemannian submersion, or So Riemannian submersion, which means that the orthogonal space to the leaves carries in an invariant metric, so that if there's a good quotient, you can project it down and it induces on the quotient the metric, which then would be the dynamics on the reduced phase space. Okay. Let me mention as an aside, so there are these two extreme cases of singular Riemannian foliations, which are isometries and regular Riemannian foliations. It seems to be the case that this notion of a singular Riemannian foliation is more restrictive than the traditional one, even if the singular foliation is algebraic, as mentioned before. So with my other student, Hadi Nahari, we looked at a famous example of a so-called non-homogeneous singular Riemannian foliation, so one which doesn't have a constant dimension of the leaves, but is not generated by isometries, and it's given by the tonionic Hopf vibration. And we could show that if one stays in an analytic setting, so that everything, the vector fields are analytic, and we can find a singular foliation there with analytic vector, so even polynomial vector fields. And if omega AB is supposed to be analytic, real analytic, then this is not a singular Riemannian foliation in this sense. So that's actually also a bit a call for trying to understand it better, because this type of singular Riemannian foliations can be gauged. So there's a gauge theory for them. And the interesting ones would be precisely those which are not coming from isometries, where you can use the usual gauge theories. And if it's regular Riemannian submersion, maybe still be of some interest, but it's certainly much less interesting than a non-homogeneous example. Okay, so much for this. And now let me start going to a formulation of this system in the BFV setting. And for that, I start with a small part about the singular foliations. So in some other work with Camille Laurent-Jambou and Sylvain Lavaux, we constructed, we showed that any singular foliation in this sense, at least if it's locally real analytically generated, or if you assume that there is a resolution of the module F, carries a Lie infinity algebroid structure which characterizes this singular foliation, and which is in some sense unique, so it's or universal algebroid. So this is associated to singular foliations, and let me use this setting to construct the BFV phase space and the BFV charge, a bit in the spirit of what I said before about this AKZ theory. So there is a Q there, and it seems to be a good candidate for a BFV charge after a reinterpretation, and a reinterpretation just in the way we had, because this Lie infinity algebroid, as I'm going to say in a second, corresponds to a vector field on some graded manifold, and so I can view it as a function on the dual bundle, the cotangent bundle, and that is precisely the cotangent bundle of a graded manifold is precisely the setting we need for BFV phase space. But it may be that also, like like I think it is true in the AKZ situation, that also here maybe the cohomology is not always correct, and that is something we have not yet studied. But we have this one allegedly so simple example of rotations in R3, which teaches us one lesson after the other. And just 2 days ago, we found out that there may be one wheel to turn and this part. I will talk about this at the end. So let me now start this. I see, I should maybe hurry up a bit. So, and in general, so given a singular foliation, F, we need to assume that it has a resolution by vector bundles, like by sections in vector bundles like this. And in general, this can be much longer, and you get a Lie infinity algebroid, but we will assume here that it stops at degree 2. And so this one map is often called rho, this map is called T. And this, on the level of sections, is supposed to be an exact sequence. So it's a complex in particular, but also there's no cohomology. It does not mean that this complex is exact. So this is not necessarily exact. So the talks are 1 hour, is it correct? And it's like 5 minutes later we started, or I forgot.
Yes, exactly. I think, yeah,
okay,
you have more than half an hour.
Okay, good. So let me give this example of, I changed the example of rotations in this setting. So there M is equal to R3. E is 3-dimensional, rank 3, I want to say, and F is rank 1. And let us call the local basis in E like EA, and there's one basis vector which I call B in F. So this is the local basis in the sections, and then we have this map. Here's the map rho, here's the map T. This map rho usually is called anchor map. So rho of EA are just infinitesimal rotations. So it's epsilon A, B, C, X, B, D by D, X, C. In this example, A and I indices and lower and upper indices are all the same because we have this canonical flat metric on R3, which we will use also as our Hamiltonian. So rho of A is these angular momenta, essentially operators from quantum mechanics. But as you see, if you take XA of them, if you contract them with XA, this is identically 0 due to the antisymmetry of epsilon AB. So there is a kernel which we can obtain by saying that T of, sorry? Was that question or no? Okay, so T is a map from F to E, so it's just even like this. And then, as from what I just said, it is evident that the composition of T with rho is 0. However, there is a cohomology at degree -1. So we will say the E is of degree -1, F is of degree -2. That's easy to see because at the origin, you see that rho maps everything to 0. On the other hand, the image of T is also 0. So at the origin, there is a cohomology which is all of R3 in this sequence, which I will call epsilon. So in this sequence, epsilon at degree -1, there is a cohomology, whereas on the regular parts it's not. And these type of cohomologies actually are important in characterizing the singular foliations on the mathematical side. And these Lie infinity algebroids, they live a bit from this difference of the exactness of this sequence on the level of sections, but the non-exactness below. And you can, on singular leaves, then find generalizations of so-called isotropy Lie algebras, which are generated or attached to singular foliations in the higher sense. So you get like higher Lie infinity algebras, isotropy Lie infinity algebras on singular leaves, which can be used to characterize the leaf. Okay, so this was the example. This is the setting, and what we proved with Camille and Sylvain was Laurent Jongou, Sylvain Lavaux, and myself, that there exists a degree +1 vector field squaring to 0 on so degree +1 on the graded manifold consisting of this in general infinite sequence, but in our case it will be just E shifted by 1 plus F shifted by 2. So you see here we have degrees, coordinates of degree 1 inside. Let's call them psi A, and we have coordinates of degree 2 inside here. Let's call them BI. And the indices run over the respective ranks of these two vector bundles. And the main feature here is that Q squares to 0. And okay, there's also the part that this is in some sense unique. And this sense is in the homotopy of in the sense of homotopies of Lie infinity algebroids. Now the idea is to say that, as I mentioned already before, so we choose our BFV phase space. We choose to be, let us call this space here M curly M in the notation before as the cotangent bundle of M with M as above. And we reinterpret this vector field as a function on T star M in the same sense as you mentioned before. So QBF we put, as you did before, we identify with the charge Q, the vector field Q, sorry, and we assume here that this is a good choice.
I'm sorry, can I ask a question real quick?
Yeah.
So E and F, you said were products of R3.
In the example.
Respectively
in the example.
L. Yeah, in the example. But when you shift, are you shifting just the R3 fiber, or are you shifting everything?
Just the fibers. So,
okay, so
the coordinates
them
X.
as vector bundles.
Sorry?
You look at them as vector bundles over M, and you're shifting the fibers.
Yes.
Okay, thank you.
Yes. So there's still the coordinates x, which will be the classical coordinates, still live in M, and they have degree 0. And then in addition, we get these coordinates xi of degree 1, which are the ghosts, and the b's are the ghosts for ghosts. And in this rotation example, there's one ghost for ghost, at least in the current formulation. So, and let me write the most general such a vector field just to have it written. So there's in front of pi, which is the same as d by dxi, we need degree 1. So there's the only degree 1 variable is psi a. So we have one coefficient here, which is rho ai. And rho ai of x is the same as this vai of x we had before. Move this a bit down. So these are these vector fields. So these were the quantities entering entering I mean, in the definition of the system we have. So and actually here you also see the constraints are, maybe I should show it again. So this is just the GA, and in the introduction I told you that this BFV charge starts with ghosts times the constraints. So this is the first part, which works well. Then there is a second, then there's a continuation of this. There is this minus a half CA BC psi B psi C, and there is a pi A here, which is the momentum conjugate to the xi's, but there can be also a contribution of degree 2 coming from the degree 2 variable, and there is precisely where the map T, where the map T enters. So here's the map T we found from before. So this is the map T, which enters here. Here the structure functions of these vector fields or of the constraints as on ones. And then we still need to write the terms which are proportional to the degree -2 vector field d by d eta, and this okay, this is just some parameterization which you used somewhere else. So there are either 3 xi's here and some h, which I call now small h. Do not confuse it with the Hamiltonian, but it is something like it's a bit related to the 3-form h in current algebroids. And they have eta I, eta j here, and psi a. And that q squares to 0 actually means that this becomes a Lie2 algebroid structure. So the CABCs, they generate a bracket on E of sections on E, but its Jacobi-eta is not 0, but actually it's T of this H, where the H you see takes 3 sections in E and gives a section in F, and then you apply the map T to it, and it's supposed to be, or it turns out to be, the Jacobi-eta, and this is all inside q squared equals 0, or the first master equation, which is QBF in the BFV bracket is 0. So as mentioned, so this defines a Lie2 algebroid structure on this curly M, or also on its cotangent bundle. And certainly this structure is not uniquely given by the singular foliation. So there's some choice to take, but as we showed in the theorem with Sylvain and Camille, in some sense, this choice is unique. In how far this is like always an automorphism in the BFV sense, we haven't worked out completely. Some parts one can reproduce. So for example, let me just, because it does play some role, look at the following coordinate transformations, which play some role. So if these degree 2 variables, I can also shift with a quadratic expression in the degree 1 variables, like this. So there's a degree preserving map on this curly M, which by the way does no more respect the splitting into E and F, but if I view curly M in 1, it is fine. And it turns out that like this H, which I wrote up there, changes essentially by dB, but this D is not a differential, and it's an exterior covariant derivative and so on. But it's still something important to observe. And one thing which actually you see from this line here is that if I change eta like this, then the structure functions will change. Let me show you how they change. So this induces, among others, like the H changes by something like dB. The structure functions change as follows. So the CABC go to CABC plus or minus, I don't know, TAI, BI, BC. Okay, and that is also something important to observe. If I go back to the beginning, if I look at these vector fields here, as a physicist, one is used that the CABCs, they are given, but if actually if one reflects about this, they are not given in this way. There's an ambiguity in them, because at a given point, the VCs, they don't need to be linearly independent. And then we can add anything to C with the upper index C, which is 0. And in fact, like for example, in the angular momentum situation, I can add anything proportional to XC, because this VC were these rotations, and we contract with XC, this is 0. So we know certainly the angular rotations in R3 have only 2-dimensional orbits in the generic part. And so there are actually at each point only 2 vector fields which are linearly independent to generate the orbits, the leaves of this singular foliation. And that gives this ambiguity in the structure functions. In the case of rotations, there's a certainly preferred choice. So in the case when we have groups, the group actions, we can always choose them to be constant, and that's a preferred choice. But in general, we don't have this preferred choice, and that's an ambiguity which is in the game. And these transformations, which I mentioned below, precisely captures, under the assumptions of this resolution, all the ambiguity I have in the choice of CABC. Okay, so let me go back there. So this is precisely this ambiguity, what we have. Okay, so much maybe, oh, the time is really running. I see. So I think I need a kind of emergency program now, which okay, I see. So the Hamiltonian, so we have now by construction this solution to the first master equation. What we now need is a solution to the second master equation, this extension of the BFV Hamiltonian. And there the observation is that our BFV charge is linear in the momenta, and the BFV bracket is degree 1 in the momenta. So the Hamiltonian vector field QBFV, which is generated by this charge under the BFV bracket, is degree 0 in momenta. So that means that we can identify every extension HBFV we can identify with some I don't know, call it a bit different, HBFV, no, maybe I just call it H, with some H in the symmetric bivector fields on M. So that's an important part. That's a consequence of this choice of this BFV charge, that it doesn't change the number of momenta, so we will always stay inside this with any extension, or we can add something in some other degrees, but it will not talk to the original classical action, classical Hamiltonian H. So, and then the condition one has here is that the Lie derivative of this vector field Q on M should annihilate this H. This is now equivalent to the second master equation in this setting. Okay, I wanted to say a bit more about what these HQ structures, how we like to call them now, would be, how they look like. In particular, under the assumption that one has in the lowest degree a metric, it turns out it equips these vector bundles, like in our case E and F, with a connection. So any HQ structure, any H structure in that sense, or any HBFV automatically comes with a connection. So you saw before that this QBFV induces several structures, like algebraic structures like Lie infinity algebras or L infinity algebras over the singular foliation. And here we get additional geometrical structures on these vector bundles by connections, then some tensors which measure the compatibility of the connections with these brackets. We call them S, maybe I come below back to them, and so on. But now the time actually is running a bit, so let me go to a central sequence which turns out to govern the extension, which is constructed out of the sequence what I called epsilon before, which has this E, F, and Tm inside. And it looks as follows. Let me put this slightly to the left. Let me delete this 0 here. So there's a 0 on the left, but let us gain some space here. Like this, and this sequence can be understood as taking this original sequence, shifting it by 1 to the right, taking the tensor product of the two complexes, this gives a new complex, and taking a symmetric graded symmetric sub-complex of it, and it's this one. So that's how it is. And this complex governs now a lot of different things in, this is a central complex which governs a lot of different things in the geometry of these QH structures, as well as the BFV extension of the Hamiltonian. In particular, if it has no cohomology, then a BFV extension of the Hamiltonian is guaranteed. So cohomology. So one statement is, as mentioned, if H delta is 0, so delta is the differential in this complex, then it implies that there exists this BFV extension. A second application I wanted to say some more. There's some geometrical applications, but let me come back to this equation that the Hamiltonian H classical with GA was omega A B times GB. Now remember that this GA were linear in the momenta and H classical is quadratic in momenta. The Poisson bracket kills 1 degree of the momenta, so the right hand side is degree 2 in the momenta. So let us just write this out, what it means. So this is omega A B I of x rho B J of x, and then we have Pi Pj here. And now one may ask, for example, about the ambiguity of one may ask about the ambiguity in the choice of these omega ABs, like we did before for CABC. So if you have the ambiguity in the choice of this omega AB, there's also an ambiguity. And so let's call it the ambiguity delta omega AB. So if I have one choice, then I can take a second choice. And it turns out that this condition, if you see this omega AB has, so this delta omega B is always a tensor. So, so we always look at sections in the cohomology in the sense of sections that I should have said. So this H delta is again in the sense of sections. And we have here degree 0, we have here degree -1, -2, and so on. And now the cohomology takes place in this degree -1. So it is because yeah, I should have said that you can always tensor with any other vector bundle, the whole sequence. So if it was exact before, it stays exact on the level of sections. So this lower index A doesn't play a role. And then it turns out that this delta AB is closed. And that's precisely, this delta closed is precisely this condition that if I take two different choices of this omega AB, take the difference, then the left-hand side is 0. And this delta omega B needs to be annihilated by the right-hand side. In particular, you see that this is a symmetric bivector, so it indeed lives in S2 Tm, and this map delta in this case is just the map rho on E to Tm with the subsequent symmetrization. So if for example, if H -1 of delta on the level of sections, I should say, is 0, then one can parameterize the ambiguity in the connections by as follows. So it's omega, okay, omega AB is equivalent to omega AB I wrote it somewhere, so there should be this index I here still. plus one part coming from F tensor Tm. So it's TIA psi BII plus rho CI MBAC, and that's antisymmetric. So, and if the cohomology is non-trivial, then there's more ambiguity. Yeah, so that's in particular this first part about the existence is one of the main results. And in the last 2 minutes, maybe I should look at examples, and it's a bit short for examples. I actually plan to have several examples, so I'm not yet used to this online Blackboard talks. So one would be like Tm and like F equal to all of Tm. Like you gauge away everything, and then this HBFV still has some interesting geometry. So it has this part Gij, and you have here these covariant derivatives of a connection, and then you have some curvature term and some torsion term here. When the connection actually is not metrical necessarily, but has something with torsion here. So this is the ambiguity. And if you choose the Levi-Civita connection, then the second condition is empty, and you still have some curvature contribution to the Hamiltonian addition for the BFV extension. So there's certainly some psi, psi, pi, pi in the game to make it work. Then we have a more complicated example, which is not the most general one, and we figured out under what condition this this does satisfy this master equation. And let me finally come to the case of back to the case of rotations. There the situation is that H classical, which is a half p vector, so it's a constant metric, it doesn't have a BFV extension in the above sense. So it's obstructed. So this first cohomology class is relatively easy seen to be non-zero. It's actually given by a covariant derivative of this map T viewed as a section E and F star. So this one turns out to be dxa tensor EA tensor dual basis of F star, which was one-dimensional. And with the metric, we can identify it with this one. And if you apply delta to it, then this is zero because this EA becomes the rotations, and then you have a symmetrization over the vector fields. So with the epsilon tensor, this gives zero. But you can easily see that nabla T is not delta of anything, because delta was mediated by rho and by T, and rho and T both vanish at the origin. That's why there was this cohomology are free at the origin. So it cannot be of this form, because you see nabla T is just constant. So that proves this. However, like there's maybe I can postpone like some more remarks about the rotations to the questions, because you made some observations just 2 nights ago how one could continue this. Okay, thank you very much.
Thank you.
May I ask a question?
Yes, please.
Thomas, so just about this last example, example of rotations. So, I mean, your Hamiltonian now is the usual P dot P, right?
Yes.
If your Hamiltonian were X dot X, this would work, right?
Precisely.
Work here.
Yeah, that's
so in this example, you can
my remarks.
Yeah. So in this example, you can simply switch P and X now. P as a base.
Precisely.
Right? So,
precisely. That's the point. So,
this would work, right?
Precisely. That's the point. So there are. The question was if this BFV charge is the right one, and it seems that the rotations suggest that. So if you look at the BFV charge in this example, let me see if I wrote it somewhere. But in this example, the BFV charge is psi times angular momentum, so it would be x times p. Plus a half psi inner product psi vector product pi, and here we have eta x inner product pi. So that's this choice, but one could also, you see that the first part is completely symmetric with respect to x and p, so you can also in principle put here p vector.
Exactly. Yes, and then this would work.
And then actually there's nothing to extend. Then it just commutes with the classical Hamiltonian, and
yes.
In that sense, now HBFV would exist. However, the question is if this would be a better choice. It seems like one should be democratic and actually permit both of them. You see that
well, actually, if you take the harmonic oscillator, probably it becomes more complicated.
Yeah, right. Precisely.
Then you need something symmetric.
Precisely. But also here the question is, and I noticed this problem precisely by looking at, we wanted to start to calculate the cohomology, because certainly without this addition, the cohomology is certainly wrong, like completely wrong. But so you need something to get the right cohomology. And in that context, I noticed, why don't we permit also P there? And you see you have the following relation. So if x is not 0, then I can write P as some function times x plus a function which vanishes on shell. Let me just by this simple identity. So which means that outside the origin, to parameterize the ambiguities, it would be equivalent to use P or X. And this is a function on D star R3 without origin. And now the situation that one of them has a BFV extension which is super simple, the other one doesn't have one, suggests somehow that probably none of the two is correct. We didn't calculate yet the BFV cohomology in this case completely, but it looks like one should add both of them. Then one needs a degree 3 ghost for ghost, which is not so difficult to find, at least if one breaks rotation invariance, and that is like where we are since yesterday a bit. And it was also still fun to look at the BFV extension of this rotation example with the above BFV charge, so with this one, in the case if you exclude the origin. So it's very fun. It gives like rather complicated formulas. You can equip, so you have some ambiguities in the choice. As mentioned, this HBFV gives like geometry on this vector bundle. So you need to choose either a connection on E or on F, or we can choose on both of them, but in both solutions we have is a connection on E and on F, and in both cases they are rotation invariant, and they have like 1 over R squares or R4 contributions. So like in the line bundle is the d of the logarithm of the radius, for example, the connection. So it's quite funny. There's still kind of funny geometry there, but we haven't yet fully understood this example. So that's why I said to Eugenia that I mean, this is very new, and we haven't yet spoken the last word, and we should probably revise our paper, trying to understand this example better. But it's one thing, what it tells us, I think, is that okay, we went back to the choice of this QBFV, and there are some rules how to get like all these ghosts for ghosts. And you see, according to these rules, outside the origin, both of them would be equivalent. And then actually, if you look at if this map T, which does generate like dependencies, if it generates also all dependents linear in the momenta, it's actually again the first cohomology of the above complex which governs this. And that's precisely not zero here. And so one needs extra ghosts for ghosts here.
Mm-hmm. Yeah. Okay, thanks. Okay, so sorry, I have to go. That I'm teaching in a couple of minutes.
Okay.
So, okay. Nice to see you.
Nice to hear you.
Bye.
Can I ask a question?
Yes, please.
Hi, Thomas. I wanted to ask about something that you mentioned all the way back in the introduction about this universal L-infinity algebra of a singular foliation.
Yes.
I was just wondering, what can you say about the history of that, of the construction of this L-infinity algebra? So I don't know much about it, but maybe you know.
I don't know what you mean by the question, the history.
I mean, who is it due? And
no, but it was a theorem of Camille Laurent-Jambou and my student Sylvain Lavaux and myself. So,
okay. Oh, I see. Sorry. I missed the citation that you gave. But did it have some prehistory? Probably a little bit, I imagine.
Well, I don't know. We actually, there were some people who apparently had similar ideas, and they looked at this also at some point, like Shengsheng Zhu. I heard. I only heard afterwards when I had proposed this project already. So, yeah.
Okay. Thanks.
Yeah. Mm-hmm. But they didn't publish anything. So.
Where is it recorded though? The result?
This one, you mean?
Yeah. No, I mean the one at the beginning, about the universal L-infinity.
Yeah, this one. So this is in Documenta, I think is the name of the journal. It's I think it appeared last year, in the end of last year.
Okay.
Yeah. Mm-hmm.
Okay, thanks.
Mm-hmm.
All right. Well, if there are no more questions, then we can thank Thomas again. Thank you very much. It was really nice talk.
Yeah, I hope to see you soon in real life again. Maybe this summer, who knows?
We can invite you for the updates about
that would be nice.
this work.
Yeah. I mean, we're probably in the Schrödinger Institute, so it's not so far away. Yeah.
I see. So we can.
It would be nice.